Welcome to my workshop. I'm Jim. Today I'd like to show you how to limit inrush current using a soft start relay. This is a power supply I'm working on. It rectifies 115 volt AC line voltage from an outlet on the wall directly into a capacitor. The line voltage is a sinusoidal waveform with an RMS voltage of 115 volts. The RMS voltage is the equivalent constant voltage that would deliver the same power into a resistor as the line voltage. The peak voltage on the line is larger than the RMS voltage by a factor equal to the square root of 2. The peak voltage is 163 volts. The line voltage is rectified by 4 diodes. It doesn't matter whether they're individual diodes or packaged together in a bridge rectifier. The diodes conduct in pairs. One pair conducts when the top end of the line voltage is positive with respect to the bottom end. The other pair conducts when the top end is negative with respect to the bottom. This is the storage capacitor. It's 540 microfarads. Both phases of the rectified current charge the capacitor up in the same direction, with the positive voltage at the top end. At the peak of every half cycle in the input waveform, the capacitor will charge back up to the peak voltage, 163 volts. In practice, a couple of volts will be lost due to the forward voltage drop over the diodes, but that's hardly noticeable when the rectified voltage is this high. The load resistance is 5,000 ohms. We can calculate the power this load resistor will dissipate once the capacitor is charged up to 163 volts. Power is the square of the voltage divided by the resistance, or about 5.3 watts. When the on-off switch is closed, current will flow through the capacitor and one pair of diodes. The only resistance in that pathway is the forward resistance of the diodes, which will be very small. This low resistance will allow a huge current to flow. The surge in current will last only until the capacitor is charged up to the peak voltage, which will probably take 1 or 2 cycles of the input alternating current. But the current will be enormous, many tens of amperes. It wouldn't be unusual for fuses to blow, or wires to melt, or diodes to explode. This surge is called an inrush current. The simplest remedy to inrush current is to intentionally insert some resistance into the circuit. Here I've added a 200 ohm resistor. No matter which pair of diodes is conducting, the current will have to flow through this resistor. The worst case happens if the on-off switch is closed at the very instant that the input voltage is at its peak value of 163 volts. Since the capacitor is discharged at the start, the 200 ohm resistor will experience the full 163 volt drop. The instantaneous current will be 163 volts divided by 200 ohms, or 820 milliamps. That's comfortably under 1 ampere, and the diodes can be sized accordingly. The question is, what will be the steady-state voltage once the capacitor charges up? Let's assume that the 200 ohm series resistor and the 5K load resistor act like a voltage divider and divide the 163 volt peak voltage between themselves in the ratio of 200 to 5,000. The voltage drop over the load resistor will then be 163 volts multiplied by the fraction 5,000 divided by the sum of 200 plus 5,000. That's 157 volts. But that doesn't happen. The series resistor and the load resistor do not constitute a voltage divider. To be a voltage divider, the same current has to flow through both resistors, and that's not the case here. Different currents flow through them. This graph shows the current which flows through the load resistor. It's constant, at least within the scale of the plot, at about 28 milliamps. On the other hand, the current flowing into the capacitor is not constant. As in any rectifier circuit, the capacitor is topped up in bursts around the peak of the input waveform. Since the frequency of the voltage source is 60 Hz, the peaks occur 120 times a second, spaced apart by 8.3 milliseconds. This black trace is the current flowing through the 200 ohm series resistor R1. Current flows through it only near the peaks when the capacitor is being charged. Current flows through the resistor in one direction when one pair of diodes is conducting, and flows through in the other direction when the other pair is conducting. The peak current flowing through the resistor is 115 milliamps. Since the capacitor only charges in bursts, a lot more current has to flow in during the bursts than flows out continuously into the load resistor. The surges in current through the series resistor lower the maximum voltage to which the capacitor can charge. It charges up to only 138 volts, which is only 85% of the 163-volt peak available from the source. Furthermore, the voltage now depends on the load. If the load resistance decreases, more current will be needed and the capacitor's voltage will fall even more. One alternative, which sounds promising, is to replace the series resistor with a different kind of resistor, one which has a negative temperature coefficient. In a normal resistor, the value of the resistance increases slightly as the temperature goes up. Things work in reverse in an NTC resistor. At room temperature, an NTC resistor has a high resistance. This would be the case when the circuit is first turned on. The high resistance would limit current flowing into the capacitor. Then, as the NTC resistor heats up, its resistance goes down. In theory, this sounds perfect, but there are a couple of flies in the ointment. The difference between the cold resistance and the hot resistance is not as big as one might want. Secondly, the installation is very sensitive to its surroundings. The temperature profile on a breadboard will be quite different from that inside a sealed enclosure. The performance of the NTC will depend on the heat generated by its neighboring components, and so on. I'm sorry to say that I've not had any success using negative temperature coefficient resistors. An electromechanical relay is a dependable way to get a soft start. This one has PC pins and is intended to be soldered to a printed circuit board. It's about 3/4 of an inch long on its longest side. This particular one is a single-pole, single-throw relay with 4 pins. This is a bottom view of the 4 pins. This arrangement of pins is fairly common. It's called a 1A footprint. The coil is connected across the device, and the normally open contacts run along the main axis. This is a 12-volt relay. That means that the coil is intended to be used in a 12-volt circuit, and that 12 volts applied across the coil will be enough to close the contacts. The datasheet shows that the resistance of the coil is 400 ohms. The other parameter of interest is the rating of the contacts. The contacts in this relay can handle 10 amperes of current at 125 volts AC, which is more than enough for my project. Let me describe how I'm going to use this relay. I'll use a 1K series resistor to limit the current in the high voltage circuit. But the relay itself is going to be a component in a completely separate low voltage circuit. As is usually the case, the application I'm designing needs 2 power supplies. The 163 volts stored in capacitor C1 is the high voltage I need. Everything else, including this relay, will be powered by a separate 15-volt supply. The 2 contacts of the relay will be connected across the 1K resistor. Then, when the relay is energized and its contacts close, the 1K resistor will be shorted out. I used an ohmmeter to measure the resistance through the contacts of the relay when the coil was energized, and I found it to be less than 1 ohm. I'll let the capacitor charge up through the 1K resistor for a few seconds before closing the relay. I'll use a 2N2222A NPN transistor to control the relay. I'll use it in switching mode, which is to say that it will be driven between its extreme cutoff and saturation modes. I'm going to connect a 100 ohm resistor in series with the relay's coil. This will bridge the gap between the 15-volt power supply and the 12-volt coil. The same current will always run through the 100 ohm resistor and the coil's resistance, so the 2 of them do form a voltage divider. When the transistor saturates, there will be a 3-volt drop over the 100 ohm resistor and a 12-volt drop over the coil, which is just what it needs. I'll use this RC branch to control the transistor. Current flowing down through resistor R2 will charge up capacitor C2. The voltage drop over capacitor C2 is the voltage between the base and emitter terminals of the transistor. Before the capacitor starts to charge, this base to emitter voltage will be zero, and the transistor will be cut off. No current will flow into the base or into the collector either. Capacitor C2 will charge up at a rate determined by its time constant with resistor R2. The time constant is equal to the resistance multiplied by the capacitance. Here it's 27K multiplied by 0.0022 farads, or 59 seconds. Let's call it a minute. This red trace shows how the voltage drop over the capacitor will increase as time passes. The capacitor will be fully charged at 15 volts after 5 time constants, or about 5 minutes. After 1 time constant, or about a minute, it will have charged up to 9.5 volts, which is 63% of 15 volts. However, the voltage drop over the capacitor will never get this high. It won't ever get any higher than about 0.7 volts. Let me explain why. As long as the base to emitter voltage of the transistor is less than 0.7 volts, the transistor will be cut off. Once the voltage rises to 0.7 volts, the transistor will turn on. The base to emitter junction in the transistor is a PN junction, just like that in a normal diode. When the forward voltage drop over this junction is 0.7 volts, current will start to flow across. As soon as the base emitter junction is forward biased, transistor Q2 will be active. In the active mode, the collector current will be proportional to the base current. The constant of proportionality is the transistor's beta, or more precisely its DC beta. Beta will typically be about 100, so the collector current will be 100 times the base current. Note that there's no resistor in series with the base terminal. When the base to emitter voltage rises even a little bit above 0.7 volts, the base current will increase very quickly. It won't take long for the collector current to reach its maximum possible value. At that point, the voltage drop between the transistor's collector and emitter terminals will be zero, and the 15-volt supply will be applied across the series combination of the relay's coil and the 100-ohm resistor R3. That will energize and close the relay. The voltage drop over capacitor C2 will stabilize at 0.7 volts, or a little bit above. Just enough current will flow down through resistor R2 to drop 14.3 volts, but that current will make a left turn and flow into the transistor's base. Everything will be in equilibrium, with capacitor C2 holding steady at 0.7 volts. We can calculate how long it'll take the capacitor to charge up to 0.7 volts. For periods of time which are very short, the capacitor's charging curve is a straight line, like this black line. Very short is defined by comparison with the time constant. Since the time constant is about a minute, periods of time of a few seconds or so can be considered to be very short. Furthermore, the slope of the black line is known. It's equal to 1 divided by the time constant. I'm now going to redraw the charging curve for short periods of time. The time axis now extends out only to 4 seconds, and the vertical axis extends up only to 1 volt. In this entire region, the capacitor's charging curve will be a straight line with a slope equal to 1 divided by the time constant. Since the time constant is 59 seconds, the slope is 1 divided by 59. For example, it would take 3.9 seconds for the voltage to rise to 1 volt. Our target voltage is 0.7 volts. That's the voltage at which the transistor will go active and the relay will close. It will take 2.8 seconds for the voltage to rise to 0.7 volts. I simulated this circuit in LT-SPICE. Simulating this circuit isn't really necessary, but it's an easy way to make sure that things work the way they're supposed to. This red trace is the voltage drop over the main capacitor for the first 5 seconds after the on-off switch is closed. The relay closes at just under 3 seconds. At that time, the capacitor is charged up to just over 100 volts. I've now overlaid a black trace showing the current flowing through the 1K series resistor. This is an alternating current, but the cycles are so short that they've merged together on the plot. When the on-off switch is closed, the maximum current is about 160 milliamps. Note that the vertical scale showing current is on the right-hand side of this plot. When the relay closes, the 1K resistor is shorted out and the current flowing through it immediately falls to zero. One benefit of constructing a simulation model in LT-SPICE is that it becomes an easy matter to see the effect of changing component values and to zero in on a satisfactory charging profile. For protection, two more components should be added to the circuit. One is a diode wired across the relay's coil. When the transistor goes into saturation, current will start to flow through the coil, and the magnetic field that's set up will close the contacts. Diode D5 won't do anything, since it's reverse biased when the relay is engaged. It does its work when the power is turned off. When the transistor stops conducting, the magnetic field in the coil will collapse. The collapsing field will try to generate a current in the same direction and amplitude as the current which just stopped flowing. Diode D5 provides a pathway for that current to flow out of the coil, around, and back into the coil until the resistance in the wiring allows the energy to dissipate as heat. Without this escape path, the current would have no choice but to flow down through the transistor, possibly causing damage. The second component is added to protect you. In many cases, the load resistance will not be permanently connected to the power supply at all. Instead, there will be a connector to attach wires leading to the load. If a load isn't connected, then the main capacitor will remain charged at 163 volts long after the on-off switch is flipped off. The solution is to add a high-value resistor whose only purpose is to discharge the storage capacitor after the circuit is powered down. It needs to be a high-value resistor because it will also drain power when the circuit is being used. I used a 1 megohm resistor for discharging. A quick calculation shows how long it will take capacitor C1 to discharge through the discharge resistor. The time constant of discharge is the resistance, 1 megohm, multiplied by the capacitance, 540 microfarads. The product is 540 seconds, or 9 minutes. The voltage will have decreased by about 2/3 to a safer level of about 50 volts after one time constant. If this is too long for your project, consider using a smaller resistor here, perhaps 100K. This is the printed circuit board on which the soft start circuit is mounted. The board isn't complete yet. I've only soldered the two power supplies into place. The 163 volt supply is located along the top of the board. The 15 volt power supply is at the lower left. It has its own transformer and uses a 3-terminal regulator. The operating circuit is going to go in the lower right. The relay is located in the upper left corner. It's right beside R1, which is the 1K current limiting resistor. Note that R1 is physically large. I used a 3-watt resistor. Recall that the current flowing through R1 at startup is about 160 milliamps. Although that current decreases with time and stops entirely after 3 seconds, this resistor is still subjected to a hefty jolt. If 115 volts AC is applied to a 1K resistor on a continuing basis, the resistor will absorb power equal to 115 squared divided by 1000, which is a little more than 13 watts. We don't need a resistor that big, but a standard quarter-watt resistor is probably too small and could explode on startup. I used a bridge rectifier instead of 4 individual diodes. This rectifier is a GBU6K. The GBU part of the name refers to the package, which has 4 inline pins. The body is thin and it's oriented vertically, so it doesn't take up much room on the board. The numeral 6 in the name tells us that the rectifier can handle 6 amperes of continuous current. The K is a code for the voltage rating. This rectifier can withstand reverse voltages up to 800 volts. The 2N2222A transistor is the small metal can. Capacitor C2 is the 2200 microfarad timing capacitor. Notice that I've mounted it lying on its side. This printed circuit board is subject to a physical constraint that it must fit inside a slot which is only 1.5 inches high. To keep the height under that limit, I've had to mount some of the capacitors on their sides. The main storage capacitor is 540 microfarads. It's built up from two 270 microfarad capacitors wired in parallel. You can just make out the 1 megohm discharge resistor, which is mounted between the two 270 microfarad capacitors where they meet up. Diode D5, which protects the transistor from the coil's magnetic field dissipation, is mounted close to the relay and can hardly be seen in the shadows. I've now set things up to do a live test. I've attached a power cord from the 115-volt wall socket to the appropriate connector on the printed circuit board. I've soldered and taped a toggle switch in line with the power cord to serve as a temporary on-off switch. And I've attached a voltmeter to the pins of one of the main storage capacitors and set the range on the voltmeter to 250 volts DC. I'll turn the power on now. If you listen closely, you will have heard an audible click when the relay's contacts closed. The voltmeter's needle followed the voltage, slowly at first up to 100 volts, and then it jumped the rest of the way up to 160 volts when the relay engaged. Everything works the way it should. That's all for today. Thanks for watching. See you next time.